fluffs out at 0 when it transitions from a liquid to a solid. So what was I going to say? Oh, so of course we're using this. This is the symbol for density. Density is mass divided by volume. And you guys did some of those in lab. So the density of H2O, it's a nice, neat number, 1.00 grams per 1 milliliter, density of liquid water. I'll go ahead and put an arrow there, so that means probably you should memorize that one. All right. So this actually is a little graph to show you exactly what I tried to tell you just a minute ago. If you kind of get your bearings along the x-axis, along the bottom there, we've got temperature. And instead of going from left to right, I want to go from right back to left again. So we have the warmer temperatures over here, and we have colder temperatures over here. You guys told me the transition temperature for water, the Celsius scale is 0. So as we are going from warm to cold, notice that here's water in its liquid state. Okay, we're going from warmer to cold. Its density is increasing. Its volume is decreasing, but it's becoming more dense. There, about 4 degrees, it starts to fluff out. So kind of this right here is the fluffing out of the liquid. Okay. So this is 4 degrees. And so it begins to get a little fluffier. And there, about when it crystallizes, okay, it really expands. What's this right here? Some of you guys know this little squiggle mark right here. What's that mean?
Shorten it up.
To shorten it up, exactly. That means that the y-axis, I wanted to emphasize something that could only be emphasized if I actually took a break in the y-axis. So that's crazy.
Wait, I don't get it.
So I wanted to emphasize, or the author of this graph wanted to emphasize how, like, to the nearest.
It jumps from 0.997 to 0.93180.
Yeah.
Oh, okay, so it's less.
Yeah, the units are.
The gap was like 10.
Right.
Okay.
Yep. Exactly. There's just a break there. So, but this is no small thing. You know, if you scale this up, I know this was iced tea, but if you scale this up to, these are, instead of ice cubes, let's make them glaciers. Okay? Now, what do glaciers do on the oceans? They generally float. At least they don't sink directly. Depends upon the mass we've got going on. But if they did sink, what would happen to the oceans? They would raise. They would displace the water. So we'd be screwed. So it's life's little things. So kind of left and right, all this is doing is trying to show you two same volumes. Okay, we have a styrofoam and a rock. Okay, which one weighs more? The rock. Okay, so here we have the same volumes, but of course the rock is more dense, right? So which is least dense here? Styrofoam. It's floating. Yep. What's most dense? The rock. Yep. So here are some densities of some materials listed from least dense to most dense. Remember, density is a ratio or division mass divided by volume. Volume can be milliliters or volume can be cubic centimeters. For gases, our volumes are usually liters. So this problem will be due on Friday. Fabulous Friday. We'll take a quick look. So this is what that one, the first one looks like. You're dealing with an unknown, but you know in the mat you have isolated a sample of your unknown, and you know the mass and the volume of the unknown. So of course, given the mass and the volume of a sample of the unknown, you can get the density of the unknown. And then all this is kind of a fun little thing to see which one does it match up with. one of these metals. That's kind of fun. And then the next one looks like this, where, you know, pennies are supposed to be made of copper, but how close are they to really copper? So
Depends on the year.
it depends on the year. That's true. That's what I've heard. So here we have the mass and the volume of a penny. Of course, by division we can get the density, and we're going to kind of see how it lines up with the density of copper. Okay. So that was your whole stopper and your wooden block from last week. Now you also took an egg from last week and with mixed results broke it into its 3 components and came up with a weight percent of shell, weight percent of white, and weight percent of yolk for your egg. So let's kind of remember how you did that. So whenever you guys came up with a weight percent, we can unpack, what I call unpack. We can say by definition what that weight percent means is that's the grams of component in 100 grams of your mixture. So for instance, if you guys had like, I don't know, 15.3% white in your egg, what that means is that if you had 100 grams of egg or mixture, then you would have 15.3 grams of white, that particular component. That's all that means. I call that unpacking. Unpacking weight percent. So, usually you don't have 100 grams of anything. I can't imagine a 100-gram egg. So what you guys did actually was this. This is all what you guys did. You put the mass of your egg in the bottom, and you put the mass of each of your components in the top, okay? And then to get it parts per 100, you multiply by 100%. Perfect. Now a little bit more, since we've done that lab, we know how to round, because we're dividing, or round according to sig figs and all that stuff. So we'll be working on that throughout the semester. So there's one more spin-off of weight percent. Okay, and it's called weight fraction or mass fraction. It's a very similar thing to mass percent. Okay, and it simply means the amount of component in not 100 grams of mixture, but in 1 gram of mixture. Okay. So I'm going to go ahead in a nutshell tell you what the relationship is between weight percent. It's simply this, that weight percent is equal to weight fraction or mass fraction times 100. That's it. They just differ by a factor of 100. It's the same thing. We're looking at relative amount of component in the mixture. So I said weight fraction, but like I said, notice that that really also means a mass fraction. Same thing. Okay. So I think we're going to do a couple examples. Oh, sorry, I guess there was one more little ratio up there. I don't know if I added this. But if you wanted not weight percent, but if you wanted weight fraction or mass fraction, notice that you do the same thing as you did with your egg, but what's different? You took the weight of the component divided by the total weight of the mixture. Would you guys have this on your slide? No? Yes?
I think so.
Okay. Okay. What's the difference between this and weight percent? What's that?
That is missing the times 100.
Right, it's missing times 100, that's it. Thanks. Okay. Okay, so let's work a couple problems. A sugar solution. Okay, we talked about mixtures. This is a 2-component mixture. We just have sucrose and water. And a lot of times I will make a picture because it just kind of gives me warm fuzzies. There's my beaker, there's my liquid, and I kind of have a couple of arrows showing I'm dumping in 5.42 grams of sucrose. Sometimes pictures just kind of help spell out the situation. And then there on the right, I'm dumping in 28.72 grams of water. And then if you look at that, you're like, oh, okay, well, my total mass is adding those two together, right? Yep, and you're right. So down there, the question is, we're supposed to knock out mass fraction, which is what? Just going to be this mass of sucrose divided by the total mass. And then we're supposed to knock out mass percent. And they just differ by a factor of 100. Mass percent of sucrose in the solution. So, here we go. So the mass of the solution, so the solution and mixture are the same thing here. Mass of the solution is adding together those two masses. Yep, the total, exactly.
So 34.14.
34.14, very good, thanks Stacy. And did we round correctly there? Yes.
There's only 2 decimals.
2 decimal points. Yes, we did. And then what do we do?
You divide the sucrose by
Yep.
So 5.24.
5.24 is the sucrose grams, divided by 34.14 grams was the grams we got. And now how do we need to round?
I'm dividing so by significant figures.
Sig figs, yep. 3 sig,
Lowest is
3 sig figs, you got it. So I got a mass fraction of 0.159. So your mass fractions are always going to be, what, less than 1, right? Unless it's pure. Is that right?
And the mass percentage, we just times it by 100.
Yes. Yep, JC said, so the mass percent, should we just take mass fraction times 100? And the answer is yes. So before we do that, I'm going to kind of tell you, if I were to unpack this, if somebody said it was 0.159 mass percent, I know that in 1 gram of that mixture, in 1 gram of that solution, I have 0.159 grams of sucrose, that component. So that's like unpacking it, what it means.
So can you if you times that whole thing by 100 to get the mass percentage,
Mm-hmm.
it would be the top number times 100 and the bottom number times 100?
Yes,
Okay.
which is 15.9 and 100 respectively. Yep, you got it. So exactly what you guys were saying, yep. So for this particular solution, we can go ahead and piggyback on our mass fraction, 0.159, and knock out 15.9% by weight sucrose. And then we can say, what does that mean? It means in 100 grams of solution, I have 15.9 grams of sucrose. Very good. So I think my notes,
Yeah, it's another problem.
yeah. So why don't you guys go ahead and you can work with each other if you want. Go ahead and knock this one out, see what you can do. Make sure you show all your work. Okay, very good. Okay, so these were also going to be due, and actually we're going to go ahead into part 6 a little bit. But those 2 assignments will be due on Friday.
Can I put the chapter 13 problem on the same
Yes,
paper as the other two?
definitely. You can throw this one on the same paper as the other 2. And yes, it is in chapter 13. That's just how this textbook works. But they're just weight percent problems. So I do want to point out, and this gets to what we're going to be talking a little bit about today and more on Friday. You see this mg, what's mg stand for? Milligrams, very good. So I'm going to say 1 gram is equal to blank milligrams. What goes in that blank? The prefix milli, it's not 100. It's 1,000, yep. Very good, 1,000. Okay. So we're going to talk more about how do you convert 178 milligrams to grams. We're going to be talking more about that. But just right off the bat, let's all just do it just in our heads. So what do you think? I should have, by a factor of 1,000, shed less grams, right, than milligrams. So what's this? Does this do you buy this? Basically, we're going to move the decimal place over 3 places. Okay, so I better not do that. So in other words, if you want to, somewhere in your notes for question B, notice that 0.178 grams, okay, of the C6H12O6. Okay? Any questions?
You can just divide that by 1,000 too, right?
Yes, we did divide it by 1,000. Yes, exactly. And then we're going to be talking about how kind of a longer way to kind of get from, but that's exactly what we do, to get from milligrams to grams. Okay. So let's go on to, hopefully they'll let me do it.
Are we gonna work any of these example problems?
No. No, they're very similar to the 2 that we did in lecture. So you should do okay. Yeah, you add them together. Sounds like you got it. Yeah. Okay. So this topic makes me smile, and every year I do this, I try to tell students that this is an important, the word's method, an important method, and an important approach to working problems in chemistry. And it's this approach that you must use. You know, there's other ways to work chemistry problems, but this will get you down the road through the whole semester, easy cheesy, if you buy into this method. Okay, and it's the method that actually your textbook talks about. And it's called factor label, and if you're like, I try to explain to you and it doesn't work, actually Khan Academy is out there that he does I don't know how the guy's so smart, but he's got things on factor label and, okay. In order to work problems, conversion problems like from milligrams to grams, one of the things, and in fact using the factor label method, is we're going to use equivalency statements. So as I stand up here with kind of quantities equal in my left and my right hand, picture an equal sign there. Okay, so these are equivalency statements. Those are equivalency statements. And now, which one did I tell you to memorize? Inches to centimeters, exactly. Okay, and if you're like me, I have to concentrate. Every once in a while, I'll get it turned around, and I'll say 1 centimeter is equal to 2.54 inches, and I'm like, wait a minute, no, centimeter's smaller. No, 1 inch is exactly equal to 2.54 centimeters. Those other 2, if you need the equivalency statement, I will give it to you. And those are approximate, and the first one is by definition. And you're also supposed to memorize this too, okay? Within the metric system for volume, this is an exact relationship. 1 cute little milliliter is exactly equal to 1 cute little cubic centimeter. Okay, so those are 4 equivalency statements. So in this approach that's here for the semester, okay, to working problems, the factor label method is you always make sure that you have no naked numbers. No naked numbers. That's the rule number 1. Okay, so that means that as you're working problems, whether it's doodling or doing a mathematical operation, if you're working problems, you need to go ahead and slap a unit on that thing. Okay? The reason the units are so important is that it's the units that are actually going to drive the problem, and you'll see what I mean. So, no naked numbers. So those equivalency statements, we looked at 4 of them today, those equivalency statements. We are going to use those equivalency statements as conversion factors. You guys already know a lot of equivalency statements. You guys know, the first one we're going to use, what's the relationship between feet and inches? You know, 1 foot is equal to how many inches? 12. You guys know that equivalency statement. 1 kilometer is equal to how many meters? 1,000. You guys know that. Or you, somewhere in there you know that. Okay. 1 hour is equal to how many seconds? 60.
Minutes.
Whoa!
Seconds.
Thank you. 60 times 60, right? Okay. 1 hour is equal to, let's see, minutes. 60. That was what I was after. Okay. So you guys know those equivalency statements. We're going to use those equivalency statements as conversion factors, and I'll show you what that looks like. And then last but not least, we're going to, and I like to usually kind of string everything up, and I read working my problem from left to right. I like to string everything up all at once. Okay, now, before we do a problem, I'm going to remind you of something that I think we talked about the first day when I said algebra is a prerequisite for this class. And I think you guys told me how to reduce this. We are going to be ending up kind of with, these are like 3 terms, and I'm multiplying these 3 terms together. I've gone ahead and, this is called a divisor, right? I just put it in. So what if I put 3/5 times 5 halves times 2 sevenths? Okay. I didn't ask a question there, did I? So let me just say that what I usually think of is I usually kind of think of as this divisor being kind of in common between those 3 terms. Okay. And then I think of anything that's here in the top and in the bottom, what can I do?
Slash the 5.
Slash them. I love it. Cancel, cancel. Anything else cancel? 2s. Okay. Let's see. I'm not a math person, but I think that's called, you can take something and break it down into its factors, and then you can cancel them out. So this whole factor label method is we are looking for not numbers to cancel, but we're looking for units to cancel. That's it. So what would this reduce to? What ratio? Yep, that's it. Okay, that's it. So let's see how it works. And we're gonna do an example of working a problem, a conversion, okay, using the factor label method. We're gonna do one that you guys know without the factor label method. So what if I had 2.5 feet? How many inches do I have?
30.
30. How'd you get there?
I did, there's 12 inches in a foot, so I did 2, there's obviously 2 12s. So
2
12
12s?
12 is 24, and then you have half of a foot, which is 6 inches, so 24 plus 6 is 30.
Yep. So I bet we're all good with that. Okay. But I'm going to go ahead and tell you the answer is 30, and that's what it would come out of our mouths. If we're writing it, we're going to have to put a little decimal after that 0. Why did I put a little decimal after the 0? How many sig figs if I put, how many sig figs if I do this? 2. How many sig figs if I do this? 1. Okay, so that's kind of a small thing. All right, very good. So let's work that same problem, but let's apply the method that we're going to be using. So I said, well, first off, do you see where this is a conversion problem? We are going from feet to inches. 2.5 feet to question mark inches. That's it. If I was going to diagram it, that's what we're doing. So to work it, basically, all you got to do is come up with a, and you guys told me 1 foot is exactly equal to 12 inches, and actually that's what we're going to use to work our problem, to get 30, which we already know. Okay? So how do you know which equivalency statement to work, to use, to your benefit? Just whatever has their units. Like, we call the old units feet and the new units are inches. Yep. So one of the things about equalities like this is if we do the same mathematical operation on both sides, that's legitimate. So let's go ahead and divide both sides by 1 foot. So I have 12 inches over 1 foot is equal to 1 foot over 1 foot. And what's 1 foot over 1 foot? It's just 1. Exactly. So do you see where, since that's just 1, that means that quantity is also 1. What happens if I go over here and put a big fat 1 right here? Does that change anything? No. So the awesome thing is, if I go ahead and insert 12 inches over 1 foot anywhere in what's being multiplied together, that's the number 1, and that doesn't change anything either. All right. Well, let's go ahead and divide, instead of divide by 1 foot, divide both sides by 12 inches. So now we have 12 inches over 12 inches, which is equal to 1, is equal to 1 foot over 12 inches. Okay. So actually then, I took something, I call it the flattened out version, the equivalency statement, the equals statement between the old and the new units. And I basically make 2 ratios. I kind of, it's like the Pee Wee Herman where you go like this, you know, like this. Oh wait, he goes like this. And I don't know what he does, but anyway, the La Macarena. So, I just totally butchered that. But you get the point. So you can either go this one on top, okay, or you can go this one on top, okay. So it's like they are inverses of each other, and they're just great conversion factors. So that's the deal. So let's go ahead and work this problem. So what I usually do is start with the thing I want to convert, which the thing I want to convert was 2.5 feet. I usually put it over 1 though. I know it doesn't say it in most of my notes, so sometimes I try to write it in. The reason I try to write it in is I try to emphasize that I've got units of feet in the numerator and I want them to cancel. So if you look at the previous slide, notice that I'm going to put feet in the bottom and inches in the top. So I'm going to go with that one. I'm going to go with 12 inches over 1 foot. And by golly, if on your calculators you take 2.5 times 12, you're going to get 30. That's it. Oh yeah. But doing it this way, and like I said, I really usually like to have my first term over 1. Doing it this way, units of feet cancel, we're left with units of inches. That's it. But don't forget that we said that we need to round according to the rules. So, is there any uncertainty brought by the 12 or the 1? No, why? There's no decimal point, but what's the special cool thing about 1 foot and 12 inches? they're exactly equal. They are exactly equal by definition. So we don't care, we don't count here, but is there uncertainty here in 2.5? Yep. So we have to round according to two significant figures, and that's, like I said, why we actually have to hardcore put a decimal after that 0.
So an uncertain number would be after a decimal point
An uncertain number,
figure, you know what I mean?
I think I know what you're saying, and is this what you're saying? Like if we had 30.0?
Yeah.
Yeah.
The zero would be uncertain.
Yep. They would be significant. The 0 would be significant.
Okay.
And that's where the uncertainty begins, and they're both related.
Okay.
Yep. Yep. And then down here, I just kind of being silly, because what if I were to take the inverse? What if I were to take the flip? Instead of 12 inches over 1 foot, what if I put 1 foot over 12 inches? What are my units going to be here? Remember, this 2.5 feet is in the numerator. What would these units be?
Feet squared over inches.
Yep. You got it. Feet squared over inches. And that should be a tall tell sign that you just didn't set it up right. So let's do another example, shall we? This one's a little harder. Okay, I can't just think of it. I can't jump right to this. I'd have to use a calculator is my point. So in this case, if we're diagramming it, we're going to go from 5.52 centimeters to inches. Okay, so what do you know about centimeters and inches?
2.54 centimeters equals 1 inch.
Yep, 2.54 centimeters equals 1 inch exactly. Exactly. So if I was diagramming this, this is how I would diagram it. I would just put this equality over that kind of arrow. How am I going to get from centimeters to inches? I'm going to use the relationship between centimeters and inches. Exactly. Because I don't like having to think too hard if I don't have to. All right, so what's the first term going to be? I think.
5.52.
Yep, I would do 5.52, no naked numbers, centimeters over 1. Yep. And then what? So I want centimeters to cancel and be left with inches.
So times it by the 2.54s.
So, well, I want,
1 inch over 2.54 centimeters.
if I go with the 1 inch over 2.54 centimeters, then the cool thing is my 2.54 centimeters cancel. And I am in business. But like I said, this is where I would usually put this term over 1. So how do we need to round it? What do I think?
Significant figure.
Significant figures, 3 sig figs? That's what I get to. I get 2.17 inches. And I think I told you guys it's fine if you want to put calc and then say what your calculator displays, look at it one last time, and then count your 3 sig figs and write answer. And some of you guys are really good about putting a box around your answer. And then rounding your calculator to 3 sig figs. Any questions? Now, I know these are kind of straightforward problems. These are just like where you multiply or you divide by a number. But as we work more chemistry problems with more chemistry relationships, this idea of just going ahead and setting it up so your units cancel and you're left with the right units. I can't tell you how valuable that is. When I say you don't have to think nearly as hard, and you really don't, if you're kind of set it up and use the factor label methods, which you have to use anyway. Okay, so that's a good place to stop, and we'll see you in lab tomorrow with your calculators.